Today we're going to talk about another sort of motion in two dimension, and that's actually relative motion. We'll talk about relative motion, and then we'll talk about circular motion, because if you have an object that moves in a circle, this is motion in two dimension. So today we're going to talk first about relative motion, and before we talk about, get into details of relative motion, we'll put some definition for what we call it IRF, the inertial reference frame. Inertial reference frame means that you have to choose a frame to measure all motions relative to that frame. Or in other words, we have to choose a coordinate system to measure all motion relative to that coordinate system. And that coordinate system has to be either at rest, not moving, or moving with a constant speed. If that frame is accelerating, we cannot call it an inertial reference frame. So only an IRF is a frame that's either at rest or moving with a constant speed. This is the definition of an inertial reference frame. Any frame can be just a coordinate system that you choose, and that frame can be moving. For example, if I choose that chair to be my frame, okay, I'll carry it. This is the frame, X, Y, and Z. I can measure the position of each one of you according to that frame, but if the frame is moving with constant speed, or if it's at rest, I call it IRF. If it's not moving, if it's accelerating, then I call it just a reference frame. A frame that we measure everything relative to it. That's it. So this is the definition of a reference frame or inertial reference frame. So I'm going to skip that. Okay, look at this problem here. We assume that we have an airplane that flies on a windy day. The pilot wants to fly from Aswan to Cairo, and he asks one of you guys, and you tell him that Cairo is 1,000 kilometers north of Aswan. Then he take off from Aswan airport at noon time. His plane has a compass and the airspeed indicator to help him navigate. So he knows the direction, and he can measure his speed as well. The compass allows him to keep the nose of the airplane pointing north. The airspeed indicator tells him that he's traveling at 1,000 kilometers per hour with respect to air. So this is the problem. We have an airplane that goes from south to north, and we have some air that flow in that direction, east. And now the pilot has to adjust his airplane, direction of his airplane in such a way that he arrives Cairo. He knows that Cairo is somewhere in here. And he flies that way. So if he actually adjusts his airplane in that direction, the air will make him shift a little bit to the right. Right? So he has to adjust his airplane in that direction in such a way that the velocity of the airplane, okay, relative to the air along the x-axis should cancel out with the air speed. I'll say that again. If the air flow in this direction, air speed is in that direction, and if I move in that direction, I will end up somewhere in here, because the air is going to be pushing me in that direction. In order to arrive to that point, all what I have to do is to direct myself in that direction in such a way that the component, if this is the y component and this is the x component, my x component of the velocity, which is along that direction, should cancel out with the x component width of the air. If I do that, I can reach that point, which is my destination, Sharif.
That's only if the velocity of the air is smaller than the velocity of the air.
No, that's valid for everything.
You just have to change the angle. The higher the air velocity, the higher the air. We're dealing with triangle.
Yeah, what's your name? Muhammad. Muhammad is saying, well, no. Muhammad is saying, no. What you have to do is to adjust your direction in such a way that the more, Muhammad has spotted that, the more the air speed, the more you should increase your x component of your velocity.
Exactly. So if the velocity of the air, which is on the x component, is higher than the total velocity of the plane, then you're going to have an unvalid triangle.
No. You still do the same thing, but it's going to take a longer time to reach your destination. Even if you have to have your airplane aimed in pointing in that direction, and the more the airspeed, the more you point it in such a way that you have at the end you reach your destination. The more you point it that way, the less y component of your velocity, and the less the y component of your velocity, the more the time you take to reach your destination. Okay. Yeah, but in that case, the airspeed is going to be much more than the speed of the airplane, and this cannot be. Then we cannot. This is not a real life problem. Then.
So
imagine you have a airspeed that's 500 kilometers per hour. Of course, for the airspeed.
Right. So are you going to solve this with numbers?
I'm just showing you the concept first. Then we'll talk about numbers.
So
Yes.
Can when we do it with numbers, make the airplane speed and the velocity of the air the same?
Sure. But this is what I'm saying. That is not a real life problem. And in that case, if you get an airspeed that's 500 kilometers per hour, what happens?
Those don't going to crash, right? Well, maybe it's flying a small plane with 100 miles per hour.
Oh, okay. Let's assume that you have an airspeed that's 100 miles per hour. It's really huge. But still, 160 kilometers per hour. We'll see. So this is how to do it. You have bivectors. And this is a motion in two dimension again, because now the velocity has two components, then you have a motion in two dimension.
But students will actually don't add them to subtract.
Yeah, exactly. That's what you do.
But this is addition.
No. I said, now, let's talk about terminology then. Terminology. The velocity of the plane relative to the air, I'm going to call it VPA, and it's along that direction. That's what you see. That's what you see in the airplane. The pilot, this is his velocity. Velocity of the airplane relative to the air. This is the velocity of the air relative to the ground. Someone sitting on the ground notice that the air flows in that direction with that speed. The same guy on the ground find out that you're actually flying. If you fly that way directly, then you're going to drift.
Yeah.
So he finds he sees you flying in that direction. You don't want to compensate yet. So this is what you're doing, Sharif. This is what you're doing. You're flying that way, and the air pushes you in that direction. So the guy on the ground, he sees you flying in that direction. And you on the airplane, you do not notice that. You don't see it. So this is the problem. You have the velocity of the airplane relative to the air along that direction, the velocity of the air relative to the ground along that direction, and this is the velocity of the airplane relative to the ground, measured by someone on the ground. That's what I mean by relative to the ground. And if you look at this, it's just an addition of vectors. It means, if you look at this, this means that the velocity of the airplane relative to the air plus the velocity of the air relative to the ground equals to the velocity of the airplane relative to the ground. And that makes sense. Think about it. Think about it. If I travel in that direction and the air pushes me in that direction, so I will actually in real life, if someone is looking at me from the ground, he will see moving in that direction, and this is going to be my velocity relative to him, and my velocity relative to him will be my real velocity, the velocity that I measure, plus the velocity of the air as vectors. And actually, if you swim, if you try to cross the river, and if the water actually flows with some speed, you face the same problem. Guys, are you solving the assignment, or what are you doing? Will you please pay attention? Guys, I showed you the concept. I told you what is the concept of relative motion. And I want you guys to look at that problem and read it. And let's vote on the answers again, as we do, like each time. A, B, or C. You're swimming across a 50-meter wide river in which the current moves at 1 meter per second with respect to the shore. So actually the current moves in that direction with respect to, as measured by someone on the shore, and the current speed is 1 meter per second. The water speed is 1 meter per second. And you should cross that 50 meters. Your swimming speed is 2 meters per second with respect to the water, as measured by by someone moving with assume that there is someone on a boat in the water. He will be moving in that direction just with the water, and he sees you moving with a speed equal to 2 meters per second. You swim across in such a way that your path is a straight perpendicular line across the river. How many seconds does it take you to get across? Can you solve that? Who said no? Can you try? Yeah, you should figure out the direction. Yes, from the problem itself, you should figure out the direction. The 2 meters per second. I don't know.
2 to 1.
I don't know. I don't know. Maybe. You may be right. Okay, what's your name back there? Ahmed? Abdurrahman. Okay, Abdurrahman, can you tell us what are we supposed to do? Just a guess. Give it a guess. Sharif. Do you draw a triangle? What does that triangle represent? Where to start? Can anyone give me a hint? Just a starting point. Where to start? What I'm supposed to do? Put a coordinate system. So okay, that's one thing. What else, Farida?
You need to first convert them from the magnitude and angle into direction so that you can
Okay. So I have to draw them as vectors. Abdurrahman, I have to draw them as vectors. So if we want to draw them as vectors, can I do this? This is the guy, see me. The guy on the boat, see me. He sees me swimming in that direction. Makes sense. I'm trying hard to reach that point. So I keep aiming at that point, and if the guy swimming on the boat, he will see me moving in that direction. So that's the 2 meters per second. This is my speed relative to the water. That's the 2 meters per second. Here it is. Vectors, again, you said vectors. That's the vectors, that's my speed relative to the water. Okay? Someone on the ground, he sees me crossing that way because this is what I'm doing. I'm aiming at that point and I keep swimming along that line to reach that point. So someone on the ground, he will see me swimming in that direction. So this is my velocity relative to someone on the ground. And this is the velocity of the water. This is the 1 meter per second. And actually I know that this component of my velocity, it has to be 1 meter per second in order to cancel out the effect of the water flow. Okay? Okay, sure. Oh, this is not the wind speed. Sorry, the water speed. This is not. Okay. Again, I'll say it again. I'm trying to go along that direction. In such a way that my x component of the velocity, this is x by the way, my x component of the velocity, which is that, equals to the speed of the water, but opposite in direction. If I do that, then I'm canceling the effect of the water speed. Okay? Should I say it again? I'll say it again. This is very important. It's easy. I know relative motion sometimes it's confusing, but it's easy if you just concentrate again with me and keep asking questions. Okay? I'll do it again. I know that someone is pushing me in that direction. And what's your name? Ali. And I want to reach Ali. I want to reach Ali. Somehow I have to reach Ali. And if I just let go and agree with whoever is pushing me and I will let go of myself, I'm going to end up in here. And I will never reach Ali. So what I do is, if he's pushing me in that direction, I try to move in that direction in such a way that my component of the velocity along that direction should cancel out with the component of the velocity that he's trying to move me with. So the x component of my motion is going to be 0 and I will reach Ali. This is what I'm doing. This is what that guy is doing. So this guy, he wants to reach that point. So he will tilt a little bit to the left. And that tilt has to be calculated in such a way that this component of the velocity should equal to the 1 meter per second, but opposite in direction. Now look at that triangle. We know that vector, that's 2 meters per second. We got that vector by setting up the problem correctly. We know that vector is it has to be 1 meter per second in that direction. Can you guys calculate that? Yeah. So someone on the ground, guys, you actually see me, if someone is pushing me in that direction, and I'm trying to compensate for that by pushing him back and moving in that direction, you see me moving along that line. So this is my velocity relative to you. And you are someone just on the ground. So the velocity of that guy relative to someone, some observer, some guy on the ground is that line, that vector. So what will be the speed of that swimmer relative to the ground? It's that vector. That's the √3 meters per second. Now I move along that line. With the speed equal to √3 meters per second, and that distance is 50 meters. How long will I take? Okay? Okay, guys? This is what we call it relative motion. Sharif, and as long as we're moving with very slow speeds like this, that's not compared to the speed of light, we talk about those, we call them yes, I'll get back to that. No, not that. We call it Newtonian mechanics. But if we move with the very high speed, if those velocities are very high speed, then we talk about relativistic mechanics.
No, my point is that in the same problem,
Mhm.
if the current speed
Mhm.
was 2 meters per second,
Mhm.
then there would have been no way that this guy would have crossed.
Of course.
Yeah, that's the point.
Yeah. Yeah.
The current speed has
So-
to be smaller than
Mhm.
the speed.
That makes sense. And then in that way, if you decide that you're going to move with 2 meters per second, that means that you don't want to reach the other shore. That means that you have to put more, something that we're going to talk about later on, force, so you can actually cross that river. Yeah, true. Okay, guys, this is relative motion. Simply, this is relative motion. If you read it from the book, it's going to be more complicated. It's that. I'm not going to teach you that part. I'm going to skip that part. That's slide number 11. Slide number 11, 12, 13, 13. I'm going to skip that part. I'm not going to teach to you. I'm going to teach by example only. Those slides teach you them the theoretical part of that relative motion. If you want to read it, read it. If you want to discuss it with me, please feel free to come and discuss it with me. But I'm going to actually do it by example only, the relative motion. This is the best way I found that sometimes when I go into the theoretical stuff, it gets more confusing. Excuse me? No, I did not skip multiplication of vectors. I said we're going to use them later on, and when we need them, I will teach them. No. Are they on the slides? Are they on the slides? Are they on the slide? No, they're not on my slides. They are in the book. Okay, circular motion. If you have an object that moves in a circle, this is another form of motion in 2 dimensions. If I move in a circle, this is motion in plane, and motion in a plane is this motion in 2 dimensions. So this is another form of motion in 2 dimensions that we need to actually understand and study. So assume that you have an object. This is the object, and moves in a circle. If that circle, if the velocity of the object, if the speed of the object is constant, if the speed of the object is constant, we call that motion a uniform circular motion. A uniform circular motion, if the speed is constant. Is the velocity constant? Why not? Yeah, thank you guys. Thank you. This is very good. Because it keeps on changing the direction. At that point, what is the direction of the object? What is the direction of the velocity of the object? Tangent at that point. So at that point, what is the direction of the velocity of the object? Negative yx. Negative yx. At that point, what is the direction of the velocity? Positive x. At that point, positive y. So you see that the velocity, though it has the same magnitude, speed is constant, does not change, but the velocity keeps on changing because the direction it changes. So this is the definition of a uniform circular motion. It has a constant speed. And by default, the radius of that circle is constant. That's why it's uniform circular motion. If it's not constant, it will not be circular motion. So this is a motion in 2 dimensions, as I said. Let's do something. Let's find the components of that velocity. That velocity, obviously, it will have two components, one along x and one along y. So the position of the particle as well, it will have also two components, one along x and the one along y. So since we have a position and velocity given in a Cartesian coordinate system, we can transform that into polar coordinate system, and we know how to do that. And we know that x and y in the Cartesian coordinate system are translated into r and theta in the polar coordinate system. Right? How about the velocities? The velocity along the x and the velocity along the y should be translated to what? Should be translated to velocity along the radius and velocity along that keeps on changing the angle. Remember velocity? What is the meaning of velocity? Rate of change of displacement. So Vx is the rate of change of x. Vy is the rate of change of the displacement y. If we carry that definition to the polar coordinate system, I forgot your name. You forgot your name too. Nagy. If we carry the same definition to the polar coordinate system, guys, Vr is the change of the r with respect to time. For uniform circular motion, does r change? No. That means that for uniform circular motion, Vr has to be 0. Vr makes the radius change. It can decrease or increase. This is the physical meaning of Vr. How about omega? It keeps the angle change. In a uniform circular motion, if you have an object that moves in a circle, does that angle theta change? Yes. So in uniform circular motion, Vr has to be 0 because the radius does not change. Otherwise, it won't be a circle. And the angle theta is constant. What is the meaning of V omega is constant? The change in the angle theta is constant. What is the meaning of that? What is the meaning of angular velocity is constant? It moves equal angles in equal times. So if it moves 30 degrees in 1 second, the next 30 degrees, it will move it also in 1 second. The third 30 degrees, it will move it also in 1 second. This is the meaning of constant omega. Because constant angular velocity. From now on, in a circular motion, we'll talk about angular velocity. And the meaning of angular velocity, the angle change with the time. That angle. Ask. W, omega. Okay, guys? Okay, good. I'm going to skip that. I will get. This is the most important part. S equal r theta. S, what is S? The arc length, which is, this is the linear displacement, by the way. S. Now I'm trying to relate S, which is the linear displacement, to theta, which is the angular displacement. Now we have two kinds of displacement in a circular motion. If I move in a circle, arc, like this, then I moved along that line, which is an arc, but it's a line, then I have moved a distance, we call that linear displacement. And I made an angle with my initial position as well. So I made an angular displacement. Is there a relation between them? Do we have a relation between angular displacement and linear displacement? Let's find out. I'm going to draw a big circle. The particle starts from here and it will move a very small angle. I'm just enlarging. This is should move in here, but I'm going to enlarge that, magnify it. It will move at a very small angle, theta. Theta is almost zero. It's 0.000000001. It's almost zero. Theta is very small. And if theta is very, very small, this is almost a line. This is a line. This is going to be a line. Not really an arc. It's an arc, but it will look like if it's a line. And this angle is going to be 90, and this is going to be 90. Almost 90. Almost 90. Look at that triangle now. Look at that triangle now. This is only, I'm going to choose theta, very small. Okay? What is the tangent of the angle theta? This is r, by the way. This is the radius of the circle. This is the radius of the circle, and this is the green part is s, the arc length. What is the tangent of the angle theta? Opposite over x over r. Opposite over adjacent. Okay, whatever the adjacent is. Right, guys? Right? Doesn't matter. Because this is 90 and this is 90. So it doesn't matter. And if you take it s over that or s over that, both of them are r. And this is only valid if theta is very small. Then S is what?
A line.
Almost a line. Yes. That's why I assume that this is a triangle. So tan theta equal S over R. That's for a small angle. Does anyone have a calculator? Okay. Try to find out what is the tan of 0.001, tangent of 0.001 small angle.
1.74 times 10
I'm sorry, in radians.
Radians?
Mm-hmm. 0.01.
0.01?
Mm-hmm. Or 01, that is. 0.01.
0.001.
Oh,
10.
okay. 0.01.
0.001.
So, guys, if you try to do it on the calculator, you'll find that for small angles, tan of the angle will equal to the angle itself. Tan of the angle will equal to the angle itself. That's for small angles. So if I carry that assumption in here, that means that theta will equal to S over R, and I can say that actually S will equal to R theta. And this is only valid for small angles.
How small is it?
Oh, that proof is only valid for small angles. Yes, I'll show it you how it works for everything.
We need to know
It's in here, in the slide.
is this a proof that we need to know?
You know, sometimes you cannot actually remember that S equal to R theta, then you should know how did I do it. This is actually for a small angle. And actually, if you look at the proof in here, it works for everything. For one complete revolution, to go one complete cycle around this, you're going to cover a distance of 2 pi r. And this is going to equal to r times the angle of 2 pi. 2 pi. Theta c is the one complete revolution. Right? What's 2 pi r? Which is the total arc length for the whole circle. That means that S equal to r theta. Distance. I'm talking about distance. Assume you have to be a little bit flexible with me on this. You did not really reach the final point. You're almost to pi. You have to make an approximation to convince you with this. Otherwise, the proof is going to be beyond 100 level. Okay, the analytical proof. Okay, guys. So now we can relate the linear displacement to the angular displacement. That's good. Let's do this. Now we have proven that linear displacement S equal to R times the angular displacement theta. Linear displacement S equal to R times the angular displacement theta. Can you remind me what is the velocity as a function of the displacement? What is the instantaneous velocity as a function of the displacement? D what? D over T, this is the average. Instantaneous, which is how I cannot hear any one of you. Only one. What did you say again? dx over dt. So if I found the derivative of s with respect to time, if I got ds over dt, this is v. This is linear velocity. R is constant. Let's do that derivative. R is constant. Does R change with the time? No. R is constant. Then you get d theta over dt. That means that v equals to R. What did we call d theta by dt? Omega. Second relation. So now we have relation that connects displacements together, linear to angular. We have another relation that connects linear velocity to angular velocity. V equal to R omega. Can you find the acceleration before I... By definition, what is the acceleration if we know the velocity? Rate of change of velocity. So again, acceleration, that's dv by dt. The derivative of the velocity with respect to time, which is going to equal to R is constant, again, d omega by dt. So actually this should be written as dv by dt, that's acceleration, linear acceleration, equals to R times angular acceleration. Would anyone like to give it a name? Simple? Alpha. So now we know linear displacement equal to R times the angular displacement. Linear velocity equal to R times angular velocity. Linear acceleration equals to R times angular acceleration. Forget that. And this is what we have proven now. V equal to R omega. And now I want to calculate the acceleration for a particle that moves in a circle. You have a circle. That's an object. This is an object that moves in a circle. Does it have an acceleration? Why does it have an acceleration? Because there is a change in the velocity. Thank you. Though there is no change in the speed, it moves with the constant speed, but there is a change in the velocity because the speed keeps on changing its direction, the velocity keeps on changing its direction, so we have an acceleration. Since the velocity change, we have an acceleration. Can we calculate that acceleration? Okay, that's what I'm going to do now. We need to calculate that acceleration. So I'm going to assume that the object starts at that point with a velocity v1, and this is the direction of v1. and it ends at that point with a velocity v2, and this is the direction of velocity v2. So if I draw v1, here it is, I just parallel it. Took that in here, that's v1, and if you draw v2 from that point, this is v2, and if you connect those two lines, this is the change in the velocity, delta v. So the blue line here, this is the change in the velocity. Am I right?
No.
Ali?
Why did you point
I just
T?
took I'm not adding them. I'm not adding them. Yeah, actually, I said this is v1, and I draw v2 from the same point, that's v2. Then I connected that line. If you add v1 plus delta v, you get negative v2. So actually, delta v is the change in the velocity. This is the change in the velocity. Okay? Okay, good. That's one. By definition, acceleration is the change, average acceleration, is the change in the velocity divided by the change in the time. So if I know how long it took to move that particle from point 1 to point 2, which is the time delta t, I now can calculate that acceleration, which is delta v over delta t. Okay, that's good. Let me finish that. I not finish the proof yet. Let me finish, then I will take all the questions that you want to ask. Okay. Okay. Let's assume that delta t is very, very small. I'm going to take you to the first or the second lecture that we studied together, guys. The limit of delta x over delta t when delta t goes to 0, this is the definition of derivative. We said that maybe in the second lecture together. If you take delta t to be very small, that means that you're getting the derivative. So if I take delta t in here in that definition, if I take delta t to be very small, then I'm not getting the average acceleration, I'm getting the instantaneous acceleration. This is only if delta t is very small, which is that definition. Okay, what is the direction of that acceleration? What is the direction of that acceleration? What is the direction of that? Let's go back to basics. Let's go back to basics. Catch. Guys, I'm going to throw this, what's your name? To Hassan, with an acceleration. To make sure that it moves with an acceleration, I'm not going to throw it. Because if I throw it, that means that I'm giving it only an initial velocity, but not acceleration. I'm going to push it till it goes to reach Hassan. What is the direction of the acceleration? Towards Hassan. Okay. What's your name? I'm going to push it till it reaches Aya. Okay? What is the direction of the acceleration? Towards Aya. I'm going to let it go. I'm going to let go of that marker, and it will move under the gravity, only gravity. And you tell me what is the direction of the acceleration? Downward. So now we know that the direction of the motion is the direction of the acceleration. That's what I have proven to you by example now. Look at the circular motion. Catch. Anyone can catch. Look at the direction. I'm going to let go at any time. Notice the direction of the acceleration. Do it one more time. always, no, it's not tangent, it's not tangent. The velocity is tangent, the acceleration. If you try to rotate this in a circle, you will feel that this is actually pulling you in that direction. This is the direction of the acceleration. So the direction of the acceleration, it's from the center out all the time. This is the direction of the acceleration. This is the acceleration of that motion. I'm not going to give it a name now. So it's from the center out. This is the direction of the acceleration for any object that moves in a circle. Good. So now we know how to calculate the acceleration, dv by dt, and we know the direction of that acceleration. That's not enough. Because I do not have v as a function of time. I do not have v as a function of time in order to get a numerical value for that acceleration. And v actually, the speed is constant. And the only thing that changes is the direction. So we cannot have a relation for v as a function of time. Look at that triangle that we have drawn a minute ago. Do you remember that? I just drew that a minute ago. Okay? This is r, vector r. And this is another vector r. Ahmed. And this is the delta r. This is this yellow part, that's delta r. Compare between those triangles. They are similar to each other. V1 and V2, both of them are equal in magnitude. So the length of V1 and the length of V2, length of that vector and the length of that vector, they are equal in magnitude. The only thing different between them is the direction. And R and R, they are also equal in magnitude. I claim that that angle here, it's the same angle in here. Can you prove it? And if I prove that that angle and that angle are the same, then those two triangles are similar, then I can do whatever I want. So this is what I want to do. Can you guys prove that this angle is equal to that angle? Let's talk about that later. I just want you to prove to me that this angle is equal to that angle. This is simple geometry. The signs? No, they are not proportional. Look at it's geometry. It's geometry. It's geometry. Look at it. The angle between V1 and delta R is V2 is equal to the angle. That angle? How do you know that they are similar? I'm trying to prove to you that they are similar. And what I'm trying to do is I'm trying to prove to you that those are similar by saying that those are equal and those are equal and the angles are equal. That means that these two triangles are similar. No. Excuse me? The sides are equal. The only thing that I have to prove now is that angle is equal to that angle. Then the two triangles are similar. Which is? And this is theta? This is theta? Okay. Okay. I can hear you. I cannot hear you. That's 90 degrees. That's good. And that's 90 degrees as well. That's correct. You're close. You're close. good approach. Yes.
Because V1 is equal to V2.
Yes.
And
Magnitude.
90.
Mm-hmm.
The angle between V1 and the angle between V1 and the line and the magnitude, the new line that goes from north to not
Yeah.
this one, but the other one above. If there was a
Would you like to come and show it to us? So we can follow with you? And you can point, do not write on it though?
This is 90.
Yeah.
This line right here, and this line right here.
Mm-hmm.
This angle should be equal.
Mm-hmm.
This therefore
Yeah.
minus this. This should not be changed.
Okay. Good. Did you get it? Did you get it? Okay. Can you prove it to me on a piece of paper? Can you prove it to me on a piece of paper? That's geometry. That's middle school. No. That's 5th grade problem. Can you prove it to me, guys? Not now. Okay, no, not now. Can you give it to me tomorrow? Can you? No? Oh, okay, Ali actually is going to prove it to us and on the board tomorrow because we have a class tomorrow. At 2. Same room. Do you want me to prove it to you guys? Yes. Who said yes? Okay. But that's not physics, that's not important, but let's do it. Though it's gonna be really boring. Excuse me? It makes sense, I understood. Yeah. Oh, what? Yeah, okay, sure. But you have to tell me, but he added something that he got you that those are equal. Yeah. The angle, that's the proof? No, the proof is, yes, you should understand what's happening. What time should we start the class? No, I'm sorry. If you want to leave, leave. Yeah. That's R. That's R. And this is V1. And that's V2, correct? And this angle is theta. This angle is 90. And that angle is also 90. Right? So, what else? What are we supposed to do? The what? I don't want to go to the sign rule because you're ثانوية عامة, right? Not many people know about the sign rule, so I don't want to actually go into there. I like that proof more better. It's just simple geometry. Do you know, guys, what is the sign rule? You all know it? Do you want to prove it? Do you want to prove it to us slowly on the board? Yes, for 1% bonus. Slowly. You're the teacher, huh? Okay.
R is equal and R is equal.
Guys, listen.
So it's going to be like this. This means they're equal. And V1 and V2 are equal.
Yes.
And if we make an imaginary line that goes like this, and this,
Perfect.
these two should also be equal. Is that correct? Okay. 90, and this angle are equal. Right? Okay, 180 minus 90 minus x, method, x will give you this angle. This one right here is the one we're looking for.
Theta.
Yes. And it will be correct here, and it will be correct here, and it will be correct here. all gonna be the same.
Yeah, it's okay. Thank you. So guys, so if those two angles are equal, which is not that important, they are equal. That means that those two triangles are similar. And if those two triangles are similar, then we can say that delta V over V1 magnitude, the magnitude of V1, which is, call it anything, it's the same magnitude of V2. I'm going to call it V. Delta V over V will equal to delta R over R. So delta V over V equal to delta R over R. What's delta R? What is the physical meaning of delta R? Which is change in the position, which is displacement. So actually delta R is the velocity times delta T. It's the velocity times delta T. So I'm going to replace delta R by its value. It's V times delta T in here. So now we know that delta V over V equal to delta R over R. Delta V over V equals to delta V delta T over R. Delta V over delta T equal to V squared over R. So I'm going to rearrange that equation. I'm going to rearrange it. So delta V over delta T will equal to V squared over R. Right? Okay. So now, if you get delta V over delta T equal to V squared over R, and you take delta T to be very small, that means that the acceleration is equal to V squared over R. And this is the radial acceleration equal to the velocity squared over R. So if you have an object that moves with the velocity speed V in a circle, what is the acceleration of that object? V squared over R. What is the direction of that acceleration? It's into the radius. It's out of the radius. Okay? We just proved that a minute ago, right? The direction. So again, now, if you have an object that moves in a circle, it will move with an acceleration equal to V squared over R. The direction of that acceleration is going to be out of the radius. Out of the center. And this is, we call it radial acceleration. So I'm going to stop here. And we're almost done. Now, guys, you can solve assignment number 3, which is posted on the web, and please feel free to come and ask me about anything in the assignment at any time.